So before actually going into the gradient descent, let me just remind you that homework 1 is due tomorrow at 4. You guys should please submit your homework solution in Gates-Hillman Center, sorry, 8001. That's Mallory Deptola's office. And there should be a box outside. If the box is not there, because maybe Mallory, I don't know whether she's having lunch or whatever, you can just slide it under her door. And there's also an announcement on Piazza that we just posted about that. So today we're going to talk about gradient descent. So this is basically the first lecture of a series of lectures on first order methods. So these are optimization methods that, roughly speaking, are only using information about the gradient of a function. So you're not going higher than the first derivative in a way. Yeah. Loudly? Okay. So just before starting with that, let me just remind you quickly that what we saw last time. So last time we had a look at the canonical form for some convex programs. In particular, we looked at linear programs. And as you might know by now, these are programs where your objective function is a linear function. So it takes the form C transpose X for some vector C, and you're minimizing over X. And your set of constraints is a set of linear inequalities or equations, I should say. So these are of the type some matrix G times X less than or equal to H, and possibly a set of equality constraints of the type matrix A times X equals B. Now, quadratic program we saw is like an LP, like a linear program, but instead of having a linear criterion of the type C transpose X, you have a quadratic criterion, typically a quadratic form. Whereas semi-definite programs are like linear programs, but instead of working with vectors, you're actually performing the minimization over a set of matrices, And conic programs, finally, we saw that this is just the most general form regarding constraint optimization problems, and it sort of captures all the other cases as subcases. So for today, we're going to look at a different problem. We are actually making in a way, we're stepping back for a second from constraint optimization, and we're going to look at an unconstrained problem. So gradient descent in the fashion that we're going to see today is an iterative method for optimizing a function that is unconstrained, and it has some smoothing properties. So in particular, it has to be a smooth convex function. Where smooth means you have to have at least the first derivative in a way. And so the problem today is minimizing this function f, where f is convex and differentiable, and the domain is going to be the entire n-dimensional Euclidean space. So we're not looking at constraints for today. Yeah. I'll try my best. Sorry, guys. Yeah. So I was just saying, for today, this is going to be an unconstrained optimization problem. So there won't be constraints. We're just trying to minimize a function f that is smooth, in the sense that it has a first derivative, and it's convex over its domain, which is assumed to be Rn. We will be denoting the optimal criterion value by f star. That's just the minimum of f of x over Rn. And the optimal solution is going to be denoted by x star. And the way we're going to try and sort of algorithmically locate the minimum of that function is by this approach, this algorithm called gradient descent. And gradient descent can be described in terms of this update rule, where you're basically, suppose that you pick an initial point in your domain in Rn. So that's x naught. Your next location will be the location where you were before, minus a step of size tk in the direction of the negative gradient. So the negative gradient is going to give you the direction where the function is decreasing the most. So if you are at a point, you want to look in that direction and make a small step in that direction, in the direction of the negative gradient. So you guys have questions about that, or the idea is clear? Is the idea clear? Okay. And then, of course, you're going to iteratively doing that, and you will stop at some point. Hopefully, you're going to be close enough to the true minimum of the function that you can stop. So here is an example where we have a convex. So this is the graph of a convex function, a 2D convex function. The global minimum of the convex function, this is actually strictly convex, so the unique global the global minimum is here, it's a unique minimum, and these are the colored curves are trajectories of the gradient descent approach. So think about, take for instance the red curve, and look at so this is going to be your initial point x naught, and you're just following the steepest direction of descent. So this would be the direction, at each point you're following the direction of the negative gradient until you reach the unique global minimum. And you can do that by picking different starting points. So for instance, the green curve is the gradient descent direction, the gradient ascent path associated to a different starting point, this starting point, and so on for the other curves. So as long as the function is convex, or even better if it's strictly convex, in a way, no matter what the starting point is, you're going to eventually locate the minimum by following this gradient descent path. Of course, if the function is not convex, now you have the problem that the algorithm becomes in a way sensitive to the choice of the initial value. Because if the function is not convex, you might have more than one local minima. And so depending on where you start, you might converge in different places. So for instance, if you take, if you look at the green curve, the blue curve, and the purple curve, these are the gradient descent path associated to these three initial starting points. And this gradient ascent path converges to this guy here, this local minimum. But this local minimum is probably is not global, and it's definitely not the same as this other local minimum of the function, or actually it's probably outside of the graph, but there's another local minimum near here, which is reached, for instance, if you initialize the algorithm by taking the red dot or the yellow dot as your initial starting value. So everything works nicely in a way for convex function or strictly convex function, but you might have troubles in a way for non-convex functions. And this is sort of expected. I mean, in this class we're doing mainly with convex optimization, so usually our functions are convex and we're fine. So we just saw that the gradient descent update rule is an update rule of this type. So your next point is going to be the point where you were before minus a step in the direction of the negative gradient. But can we sort of give an interpretation of why are we actually performing that particular update? And the answer is that you can sort of justify the procedure by looking at an expansion of like a second order Taylor expansion of the function f at around a point x. So usually that would be like f of y is equal to f of x plus the gradient of f at x transpose y minus x plus 1/2 y minus x transpose the Hessian of f at some point t x minus y plus y, some intermediate point on the line segment joining x and y, times y minus x. And I'm sort of assuming here implicitly that the function is twice differentiable for the moment when I write this expansion, but it's actually not necessary. So if you tweak this Taylor expansion by a little bit by basically replacing the Hessian of the matrix by 1 over t times the identity, what you get is an approximation of f of y, which takes the form f of y is roughly equal to f of x plus the gradient of f at x transpose y minus x plus 1 over 2t, the square norm of y minus x, right? So now you have a quadratic approximation of the function. This is not assuming that the function is twice differentiable. I was just writing a second order Taylor expansion to tell you that you can sort of get this expression by tweaking it. But you can think about this approximation of f as a linear approximation, so a linear piece, plus a proximity penalty, if you like to, I mean, like some penalty that tells you you're basically penalizing how far y is from x. So you can think about it as a proximity term. So in this equation, I'm basically assuming that we are at point x, and I'm trying to look where to go, and that will be y. And I want to go I want to pick an optimal point, y. And so what I'm doing is I'm taking a linear approximation of the function f at x, and I'm adding a proximity penalty that is basically higher as the farther I move away from x. Okay? Do you have questions about this, guys? Yeah.
Where did t come from in the first line?
Oh, the first line. So this would be. So this is basically the one way to express the exact, to characterize exactly the remainder of the Taylor expansion. For some t's, sorry, yeah, I should write for some t in 0, 1, yeah. And actually t is not a very good choice because I'm taking t to be the step size, so let's call it theta. For some theta in 0, 1. For some. Okay? Well, you'll actually see it when this is actually justifying, this is a way of, I'll come to that. The idea is that you're really trying to approximate the function linearly and adding a penalty term that's preventing you from moving away too far from where you were. And that's why you have a linear approximation of the function plus a quadratic penalty, like a proximity term. The idea is that if you want to sort of interpret it as in terms of a Taylor expansion, you can derive that by tweaking the Taylor expansion and changing the Hessian into 1 over t times the identity. Okay. But strictly speaking, I probably shouldn't even write the second order Taylor expansion because I'm only assuming the first derivative exists. But the idea is just to show you that you can derive one expression from the other in a way. Okay, so now this is if you look at this new, let's say that this new function, let's call it g of y. Now I want to see where to optimally go. So I need to minimize g of y. Okay, and g of y, notice that it's a convex function. So it's just the sum of a quadratic function of y plus a linear term, plus a linear function. So to do that, I need to set the gradient of g of y to be 0, okay? And that's equivalent to saying that the gradient of f of x, the gradient of f of at x, so I'm differentiating this first term, plus 1 over t y minus x, so the gradient for this other piece has to be equal to 0, right? And from this, if you just rearrange and make sort of write this equation in terms of y, that's going to look as y equal to x minus t, the gradient of f at x. So this is basically saying that what gradient descent is doing is you're approximating by a quadratic function, or like you're approximating your function f by a linear piece plus a quadratic penalty. You're minimizing over that approximation, and the optimal new position is going to take this form. It's going to be the point where you were before minus plus a step of size t in the direction of the negative gradient. So you guys have questions about it? Okay. Yeah, and you can call, if you want, you can call y, let's just call it x plus, to mean like my new position is going to be equal to y equal to x minus t, the gradient of f. So there is an interpretation, like a visualization of what's going on. So your function f is the thick black curve, and you are at the blue point currently. So this is your x. You're basically looking at a quadratic. You're adding this quadratic approximation to the function. So this is this function f of x plus the gradient of f x transpose y minus x plus the quadratic proximity term. And instead of minimizing your function, you're minimizing this quadratic approximation, and you're moving from the blue point to the red point. Okay? And you can think about the distance. So what's driving the distance between the red point and the blue point is this proximity term, this quadratic proximity term. So the higher t, so the larger the step size, the less you are penalizing your for moving away from x, so the larger you're going to sort of move away from the blue point. Is that clear? Okay. So what we're going to see today is how to optimally choose the step size, actually how to adaptively choose the step size when you have a function f that satisfies certain properties. And then we're going to look at the convergence analysis for the algorithm, meaning are there any theoretical guarantees about the rate of convergence of the algorithm? So how far, given an initial starting point, are you converging to the global minimum of the function that you're trying to minimize? And then we're going to look at a couple of examples. Actually, we'll be only discussing gradient boosting for regression trees, but the slides also contain forward stage-wise regression as an example. We're not going to cover it in class, but if you guys have questions, you should ask. You should definitely try and look at it by yourself, and then if you have questions, come to office hours and ask us. So it's clear that we have to pick a step size. And probably the simplest idea would be, well, let's just fix some number. Let's just take some number t and keep the step size constant across all the iterations of the algorithm. So this means let's just take tk equal to t for all k. The problem with that is that if you take the step size to be too large or large enough, the algorithm can actually diverge. So for instance, consider if this function, this is a quadratic function of x, so f of x is 10 x1 squared plus x2 squared divided by 2. You initialize your algorithm, so you pick this as your starting point, you fix a constant step size, you move, and you perform the gradient descent algorithm, so you're moving here. The first iteration takes you here, the second iteration takes you here, where the gradient is becoming larger and larger, and so the other iterations are just blowing up in a way. And so it's true, you're getting closer to the true minimum, which is at the origin, but you're never actually going to reach there. You're just oscillating to the right and to the left of it. And so maybe a 1D example might give you a little bit more of intuition about what's going on. So let's do that. So let's take, for instance, f of x to be x squared. Of course, the gradient of f is just the first derivative, so it's 2x. And your optimal solution x star is at 0. So the global minimum is at 0. Say that you take x naught, your starting point, to be 2, and you fix your step size to be constant and equal to 2. So let's see what happens. x1, if I apply the gradient descent update rule, is going to be equal to x naught, the place where I were before, minus t, the gradient of f at x naught, right? So now that's going to be equal to 2 x naught minus 2 times the gradient of f at 2, which is 4. So this is 2 minus 8 equals minus 6. So let me just plot it here maybe. So I started at 2. Oh, sorry guys. Sorry, yeah. Yeah. So I started at 2. This was my x naught. My first iteration took me at minus 6. The second iteration, if you perform the same sort of update, is going to be x1 minus t, the gradient of f at x1. This is x1 is minus 6 minus 2 times the gradient of f at minus 6, which is minus 12. So you get minus 6 plus 24, which is 18, right? Yeah. So this, I jumped from x naught to x1 on the negative side of the real line, and I'm jumping back again on the positive side, but even farther away. So it's clear that we're not converging to the global minimum here. And this is because we took a step size that is too large. So the step size being too large is basically driving me into places where the gradient of the function is becoming larger and larger. So there's no chance that we can ever converge. And you can try yourself that, for instance, if you stick with x not being equal to 2, and if you take t to be 1, you're actually oscillating between 2 and minus 2. Whereas if you take t strictly less than 1, you're actually going to converge in this case. So this is just to give you an example of what's going on. On the other hand, if you take the step size to be, what's going on when the step size is too big? On the other hand, if you take the step size to be too small, the problem is that you're never actually, of course, you're converging to the global minimum, but it's taking you too long to get there. Okay? So this is, for instance, the same example with the same function after 100 iterations of the gradient ascent. We are very far from having reached the global minimum. Of course, if you have a way of optimally tuned step size, the algorithm is supposed to work well. So, for instance, if somehow we are able to pick the step size just to be to have the right magnitude, the algorithm is actually going to converge rather fastly. Like 40 iterations is something that you can actually afford with the gradient descent, because the gradient descent algorithm is really only a matter of computing the gradient of a function. That's not very expensive in a computational sense. So 40 iterations is something that you can definitely afford. And so there's a trade-off here. Like, I pick the step size to be too large. I tend to converge faster to the global minimum, but the algorithm can be very unstable, and I can potentially diverge. If I take the step size to be too small, I have the guarantee that I will eventually locate the minimum, but it might take me too long, just too long. So we need a way of picking the step size. And what people usually do is to adaptively choose the step size by using a technique that's called backtracking line search. So this technique is using, so you have to basically choose two parameters, alpha and beta. So alpha is a number between 0 and 1/2, beta is a number between 0 and 1. And backtracking line search works as follows. At each iteration of the algorithm, you just fix the step size to be equal to 1. And while this condition is satisfied, and I'm going to explain it in a second, you're just going to shrink t by an amount equal to beta. So you're geometrically shrinking t. And as soon as this condition is no longer satisfied, you take a step according to the gradient descent algorithm with step size equal to the last t that you recorded. And so if we take a look at this condition, this is basically saying f of x plus, this is just x plus, my new location, is the value of the objective as the new location larger than the value of the objective at the location where I was before minus alpha t times the square norm of the gradient? So the question in a way is, am I decreasing the objective by at least this amount? Okay? So if not, I'm just going to shrink the step size. Probably I'm taking a too large of a step size. I'm going to shrink it by beta, and I'll check again. So when the time comes where my new objective value is smaller than the previous objective value minus this quantity, then I'm actually performing the step. And for simplicity, you can think about taking alpha just equal to be 1/2, and we will see why 1/2 makes sense when we look at the convergence analysis for the algorithm. So in the proof, it actually pops out very clearly why 1/2 can be considered a standard choice for alpha. But let me give you a sort of a visual interpretation of backtracking. So this curve is the value of the objective at your new location x plus, oh, sorry, guys, I should probably point out the following. This is taken from Boyd and Vanderberg. They're discussing it in a more general fashion, so they use this delta x. Delta x for us is just going to be negative the gradient of f, okay? So whenever you read delta x, plug in negative the gradient of f at x, okay, as stated here. So as I was saying, this is the value of your objective function at the new location, x plus t delta x, which is x minus t, the gradient of f at x, okay? So ideally, then this is plotted as a function of t, as a function of the step size. So ideally, you would like to take this step size, because this step size is the step size that gives you the lowest objective when you parameterize your new location as a function of t. What backtracking line search is doing is just telling you, well, don't be too greedy. Don't try and locate the optimal step size. Just, be happy enough if you can decrease the objective function by the amount alpha t, the square norm of the gradient of f. So you see that alpha is basically giving you the slope of these lines, which are the line that is intersecting the y-axis at f of x, so the objective function at your current location is a function of t. And as you make alpha larger, you're being more and more greedy because you're pushing this line towards this other line. You're increasing the magnitude of the slope. And so a higher value of alpha means I'm trying to be more and more greedy. I want to decrease my objective by a larger and larger amount. But really, the idea of backtracking line search is that eventually you're going to pick this value rather than this value, which would be optimal. And so you're paying a small price in terms of how much you're decreasing the objective function, but you're gaining a lot in terms of stability of the algorithm. You're preventing yourself from picking a step size that is too large and diverging. Are there any questions about this, guys? This is sort of important in a way because it's what people, yeah.
So the choices of alpha and beta don't matter that much.
Well, there are guidelines, I would say, but I don't know, maybe different people, I guess, have different feelings about that. The idea is that alpha is to be a number between 0 and 1/2. You'll see that you'll see why in the proof when we prove the convergence guarantees for the gradient descent. But beta is just a discount factor, so it's a matter of, I would say, gut feeling in a way. So you see that beta is basically telling you how fast you're shrinking your step size at each backtracking iteration. So a larger beta means it's probably taking a little bit more to locate the the step size that is actually making this condition to fail, whereas a smaller beta is shrinking t faster. So it's probably taking fewer iterations to satisfy this constraint, but you're probably farther away from picking the right step size or the optimal step size in a way. So it's really like I would say, I don't know if the other TAs have different opinions, but I would say it's mostly a choice of sort of gut, it's a matter of gut feeling in a way. But Boyd and Vandenberg books, I think there are a couple of standard choices. Definitely alpha equals to 1/2 is a standard choice, and for beta they have guidelines, similar guidelines. Okay, so this is a picture where Ryan was running the backtracking line search algorithm on the previous function, on the quadratic function that we saw before. And the backtracking is picking roughly the right step size. So we are starting from here, and we are making steps of different size. This is chosen adaptively by backtracking line search. And you see that we are converging, we are getting very close to the minimum of the function in 40 steps. And these steps are counting both the gradient descent iterations, so the actual steps that you're making with the algorithm, and the inner loops of the 28 inner loops of backtracking line search. Okay, so there's a sort of now that we're introducing backtracking line search, you have to keep track of two things if you want. Like one is the number of steps that you're making according to the algorithm, and two is the number of inner iterations that you're running with the backtracking line search, meaning the number of these loops. Okay, and this is saying it took us 12 outer steps, meaning 12 iterations of gradient descent, and 40 steps total, meaning that it took us 28 iterations for optimally choosing the step size.
What do you mean by right step size? Who knows what?
Sorry, say again?
What do you mean by the right step size? Maybe there's much better.
Oh yeah, I mean, yeah, that's definitely like probably not the right word, but the right step size meaning Ryan used to tell the following joke, taken from, I think, Goldilocks and the Three Bears. You want the porridge not to be too hot, not too cold, just right. So this is the kind of idea, You don't want the step size to be picked too large, not too small, we want it just right. And backtracking line search is actually helping you to do that. So this is about the right quotes about the right step size, basically. Other questions, guys? Yeah.
How do we translate the initial t value? Because this method can only shrink the t value.
Yeah.
So we count the value. I mean, there might be some cases the initial t is very small, so that in the next steps.
Oh, that's an interesting question. So how do why do we start with t equals 1? You mean? So actually, I've been thinking about it. I'm not completely sure about why t equals 1. I think it's just a matter of, I think it's just a standard choice in a way. But the idea is that as long as you're moving, so if you think about infinitesimally moving in the direction of the negative gradient, you are sure that you're decreasing your objective, right? So there must be, intuitively, there must be a t that it's small enough and it's decreasing my objective value. So I think that t equals 1 can be considered as a sort of a standard choice, but presumably you can pick a different initial step size. Sorry, say it again, sorry?
I think this method can only solve the divergence problem. That is, we can control t, it won't be too large, but it cannot solve the slope if the initial t is very small.
If the initial t is very, yeah, that's a good point. Yeah, I'm not completely sure about that. Like Nicole or you guys have any intuition about that?
So to solve the slow to converge problem, we're going to see another technique later. In this case, but that technique is only going to work if you have line search already in place. So accelerated gradient descent only works if you have line search to make sure that you don't go out of bounds. So that's why we're looking at this right now. The nice thing is that you can know that you're on the safe side, and if you'll be able to sense, like in practice, let's say you just use this out of the box, you'll be able to sense in practice if your initial t is too small, because it won't ever shrink, right?
Yeah. Yep.
You can also imagine a situation where if it's too small, you can increase it, but instead of increasing the you can increase it by
I'm sorry, I didn't get it. You can.
so if it's too small, you can instead of making the same, instead of decreasing it by beta t, you multiply the same to 1.5 times t and keep doing that until some condition by the
Yeah, I think it works in both directions in a way. I guess if you have a feeling that you're picking it too small, you can definitely inflate it rather than deflate it. But I would claim, though, that as long as you're moving infinitesimal, if you're making an infinitesimal step into the negative direction of the negative gradient, you should be decreasing. So I think that intuitively there must be some small enough step size for which you're still decreasing. Probably it's just too small, so it's not definitely always the right thing to do, perhaps. Yeah, but these were good questions, yeah. So we saw that. Of course, there will be another approach. You might try and actually solve the following minimization problem and really figuring out what is the optimal step size. So here you're looking at again at your objective as a function of the step size s, and you're looking along the line in the direction of the negative gradient, and you're trying to figure out what is truly the optimal step size. Thing is that, so if I go back to the picture, you're basically trying to locate this point. The problem is that most of the times, this is not usually, you just can't do that analytically. And if you try to do that and approximate it, usually in practice, you're not gaining that much as opposed to perform backtracking line search. So this is usually not advised, but there might be situations in which you are able to do that. Okay, so we can now move on to the convergence analysis for the algorithm. And so the aim of this part is basically to show that if the function f satisfies certain smoothness properties, you can bound from above the error that you can bound from above the error the accuracy of the algorithm, basically. So how larger is the objective at the kth iteration with respect to the optimal value of the objective. and you can bound it as a function of the number of iterations. So the function class that we're going to consider is the class of functions f that are convex and differentiable over Rn. And we are also assuming on top of that the gradient of f is a Lipschitz map. So it's Lipschitz with constant L. So that means that for any pair of points x and y, for any two vectors x and y, the distance of the gradient of f at x to the gradient of f at y is bounded above by this constant L times the distance of x from y. So you guys are all familiar with the Lipschitz condition, right? Lipschitz continuity. And so under these two conditions, we can show the following theorem, that the following theorem holds. So the gradient descent with a fixed step size t that is not larger than 1 over the Lipschitz constant of the function satisfies the following inequality. So this is telling you that the objective value at the kth iteration minus the optimal value of the objective is not larger than some constant which depends on the distance from your initial location to the optimal, to the minimizer of the function, divided by twice the step size times the number of iterations. So this means that your rate of convergence is of the order 1 over k. So this is just a constant, like the square norm divided by 2t times 1 over k. So I mean, maybe put it in this way. Like the theorem is saying that if t is less than 1 over L and it's fixed, f of xk minus, x star, f of xk minus f of x star is not larger than x naught minus x star squared divided by 2tk, which is big O of 1 over k. Equivalently, you can state the same result in a different fashion, but it's equivalent. You can set the desired accuracy to be equal to epsilon, okay? So if you set epsilon, you want f of xk minus f of x star to be less than or equal to epsilon, so you want to have at least accuracy epsilon, then epsilon is equal to x naught minus x star norm squared divided by 2tk, which is just some constant, let me call it c divided by k, meaning that k is to be equal to c over epsilon, which is big O of 1 over epsilon. And you can state the same result by saying if you want to achieve accuracy epsilon, so if you want f of xk minus f of x star to be less than or equal to epsilon, you need on the order of big O, on the order of 1 over epsilon iterations. So are there any questions about how to interpret the statement of the theorem? You can basically think about it in two equivalent ways. Either you can say the rate of convergence is of the order 1 over k, or if I want to have accuracy epsilon, so to get f of xk minus f of x star less than or equal to epsilon, I need to run the algorithm about 1 over epsilon iterations. Okay, so let's prove the theorem. So remember that, actually this is part of homework 1. You should have shown in homework 1 that the gradient of f being Lipschitz continuous with constant L is equivalent to saying that f of y is less than or equal to f of x plus the gradient of f at x transpose y minus x plus L divided by 2, the square norm of y minus x. This is for any x and y. Okay, so this is part of homework 1. One way of characterizing the Lipschitz of f being, the gradient of f being Lipschitz. So remember that the gradient descent algorithm is telling us that our new point y, say equals x plus, is going to be equal to x minus t, the gradient of f at x. Okay? So I'm going to plug in this particular y in this inequality, and that will give me that f of x plus is less than or equal to f of x plus the gradient of f at x transpose y minus x is going to be minus t, the gradient of f at x, plus L divided by 2 times t squared, the square norm of the gradient of f at x. Okay? So now I can rewrite this by collecting t. Well, first I can write it by making it a little bit clearer. This is the same as f of x plus minus t times the square norm of the gradient of f at x plus LT squared divided by 2, the square norm of the gradient of f at x. Okay? Then I can just collect one of the t's. Well, actually, t times the square norm of the gradient, and that will give me f of x minus 1 minus LT divided by 2 times t, the square norm of the gradient of f at x. Okay? So now here's the interesting part. So far I only collected t. The interesting part is that we can note that 1 minus LT divided by 2 times t is oh, sorry guys, yeah. Okay. Is no less than t halves for t, well, let me write it for t in 0, 1 over L. Okay, so you can check it, but like the idea is that if you plot these two functions, you have a graph that looks as follows. So this is the line t over 2, t divided by 2, and this is your quadratic function of t. Is going to be something that looks like that. Okay? So that means that when I'm subtracting 1 minus LT divided by 2 times t, I'm subtracting more than t divided by 2. So I can bound this guy. Let me put an asterisk here. So this is going to be less than or equal to f of x. Oh, thanks. Sorry, f of x minus t halves the square norm of the gradient of f at x. Okay? So far, so good. Now, the thing that I'm going to do is to substitute the gradient of f at x with the inverse formula here. So this is basically equivalent to saying that the gradient of f at x is equal to, I think, x minus x plus. Yeah, x minus x plus divided by t, right? So I'm just going to plug this expression for the gradient here. And so I'll have that this is equal to f of x minus t halves times the square norm of x minus x plus divided by t squared. Okay. This is equal to f of x minus 1 over 2t times the norm of x plus minus x squared. Okay. Now, this is another trick that we have to use. Notice that, let me put it up here. Okay, so by the convexity of f, we can write that f of x star, so at the optimal value, is larger than f of x plus the gradient of f at x transpose x star minus x. I'm just writing the definition, the first order characterization of convexity, so the function is supported by all of the tangent lines, which is equivalent to saying that f of x is less than or equal to, I'm just moving this side to the other side, f of x star plus the gradient of f x transpose x minus x star. Okay? And now I'm going to bound this term here, so double asterisk, with the bound that I just got from the definition of convexity. Okay? So this thing here will be less than or equal to f of x star plus the gradient of f at x transpose x minus x star minus 1 over 2t x plus minus x squared, the norm squared. Okay. Now I'm going to plug in the same expression as before for the gradient. So this is equal to f of x star plus x minus x plus divided by t transpose x minus x star minus 1 over 2t, the square norm of x plus minus x. So now I basically almost have, you see that this looks like a piece of a quadratic form, but I'm missing one of the squares. So I'm just going to make that appear basically. Yeah, let's rewrite it before. So this is actually f of x star plus 1 over t x minus x plus transpose x minus x star, and I'm off the screen, minus 1 over 2t x plus minus x squared. So the only thing that I'm going to do here now is to add and subtract, yeah, I probably should collect first. 1 over t, so this is 1 over 2t times twice x minus x plus transpose x minus x star minus x plus minus x squared norm. So now I'm going just to add and subtract x minus x star squared minus x star squared in the square brackets. So that is going to give me the that's going to give me the complete square. Hope it turns on again. Yeah. So that I can rewrite this as f of x star plus 1 over 2t, sorry, 1 over 2t times this piece minus the square norm of x minus, actually this piece, x minus x star square norm plus this minus the square that I just completed. So minus, that would be x plus minus x star squared. Okay, so this square is just these two pieces minus this one, and I'm adding back this guy. Okay? Questions? Okay. Okay, so now what we have now is a bound of the following type. If we go back for a second, where is that? That's here. So we were bounding f of, we have now an inequality that involves f of x plus, and we are bounding that by this quantity. So I have, now I have f of x plus, I'm just moving f of x star to the other side of the inequality, minus f of x star less than or equal to 1 over 2t x minus x star squared minus x plus minus x star squared. So this is the bound for each iteration, right? This is involving the new point x plus minus the optimal point x star. So I can now sum over the iterations and get a similar and bound the sum of these differences. So the sum over k iterations of f of xi minus f of x star is going to be equal to 1 over 2t, the sum from I equals 1 to k of these guys. So that's the previous point x, so xi minus 1 minus x star squared minus xi, my new point, minus x star squared. And this is a telescopic sum. So I'm going to retain only, so what I get in the end is going to be the first term and the last term in the sum. So this is actually equal to 1 over 2t times the first term, x naught minus x star squared minus the kth term, xk minus x star squared. And now I'm going just to throw away one of these two. So I'm just keeping x naught minus x star, and I'm bounding it by throwing away this negative square norm. So this is less than or equal to 1 over 2t x naught minus x star squared. Okay. Now I will just take the average of all these, I'll make this sum into an average. And I should probably have changed the slide now. Okay, so we are basically at line 1. And you know, since this is the optimal value of the function, these guys cannot be smaller than that. So all the f of x i's are larger than or equal to f of x star. So all these summands are positive. I'll just take an average of those. So 1 over k, the sum 1 over 1 to k of f of xi minus f of x star is less than or equal to 1 over 2k, 2tk, the square norm of x naught minus x star squared. Okay? And then we are there, because if I take the kth summand, so if I take the kth one, so the kth one is going to be the smallest of these summands, right? Because I'm progressively decreasing the function, so f of xk minus f of xk is going to be the smallest of all of my all of the f of xi. So the minimum of that has to be less than or equal to the average. Which is less than or equal to 1 over 2k, 2tk, the square norm of x naught minus x star. And here we go. So now we have the result. Any questions about the proof, guys? Oh. Okay. So one thing that I'd like to point out, though, is that if we go back here, when we bounded this quantity here by, we were trying to bound this term by, and we claimed that 1 minus LT divided by 2 times T is larger than T over 2. we got this bound, and notice that this bound is exactly the backtracking line search bound when alpha is equal to 1/2. Usually you have something of the type in the backtracking line search. You are trying to satisfy the following inequality: f of x plus is less than or equal to f of x minus alpha t, the square norm of the gradient. You see that this is just the same thing with alpha equals to 1/2. And so basically, if you perform backtracking line search with alpha equals to 1/2, and your function happens to be Lipschitz with some constant L, then you automatically get, you should expect to automatically get the right convergence rate, so 1/k. Okay? You basically had, if your function is Lipschitz and you're doing backtracking line search with alpha equals 1/2, you're going to get the rate in a way. Okay. Oops. And so the convergence analysis for backtracking, in fact, gives you that result. So if you take the same assumption, so f is convex and differentiable, the domain is still the same, and the gradient of f is a Lipschitz map, so it's Lipschitz continuous with constant L, you get the same rate for gradient descent with backtracking line search. So you see that this is, again, some constant depending on the initial point and the optimal point times 1/k. The only price that you're paying is that your constant will depend on this quantity T mean, which is the minimum between 1 and beta divided by L. So usually, if we didn't have backtracking, instead of having beta over L, we would have 1/L. And so we're just paying a small penalty in this constant when we're actually performing backtracking. But if beta is not too small, you're not paying that much. So as long as beta is not too small, you're not blowing up this constant in front of the rate. Yeah? If the so if the function was Lipschitz and not the gradient, that's an interesting question. I would say I don't know actually. We should probably ask Ryan for the one, unless Nicole or you guys have. I've only seen the result, for the Lipschitz case and for the strong convex case. So Lipschitz gradient and strong. Yeah, but for that you have to have strong convexity though to get. Oh no, sorry. No. Yeah. For oh. Sorry, can you just repeat the last question a little bit?
But I was saying that there are lower bounds, I think, which show that for just convex functions, which is assumed to be Lipschitz, not strongly, not gradient is Lipschitz.
Okay.
There is a lower bound which goes like 1/√k.
1/√k. Okay.
1/k. So it seems like what's helping here maybe is the fact that we're assuming gradient is Lipschitz.
Yeah.
But intuitively, I don't have a sense for why does assuming smoothness help the rate. It seems like going from convexity to strong convexity should help, because that says how flat the function
Yeah.
is. I don't have an intuition for why does smoothness help.
Yeah, that's an interesting question. Probably we should investigate the proof a little bit more. I'm not sure. Like out of my head, I just don't have the answer for that. But yeah, that would be an interesting question. Definitely worth discussing it more. Okay, now if you keep the same assumptions as before, but you also add the assumption that your function f is strongly convex, and that means, as a reminder, that you can subtract. This should be m, not 2 divided by 2. It's just m divided by 2. So if for some m you have some positive m here, you can subtract the m halves the square norm of x to f of x, and you still get a convex function. That means that the function f is strongly convex. So you can subtract a quadratic and still get a convex function. And if you keep the same assumptions as before, so f is twice differential. Oh, sorry. Let me start again. So let's keep the same assumptions as before and add the assumption that f is also strong convex on top of being differentiable and having Lipschitz gradient. Then you get the following theorem, that the gradient descent with fixed step size t not larger than 2 divided by the sum of the two constants, m and l. So this is the Lipschitz constant, and this is the constant for strong convexity. So the m that should be here in place of 2. You get actually a exponentially fast decrease. So your accuracy at iteration xk, so f of xk minus the optimal value f of x star, is not larger than some constant c to the power of k, the number of iterations, times some other constant, depending on the Lipschitz constant and the square norm of your initial starting point minus the optimal point, with c between 0 and 1. So that's basically saying that your rate of convergence is exponentially fast. So your convergence, your rate is of the type c to the power of k for some c between 0 and 1. Or equivalently, you can state the same fact by saying that in order to get accuracy epsilon, you need about log of 1 over epsilon iterations. So definitely a much faster rate. And usually, this is called linear convergence when you have when you have a situation where in order to get accuracy epsilon, you need log of 1 over epsilon iterations. Because if you plot sort of the decrease of the objective on a semi-log plot, so a plot where you have the number of iterations on the x-axis and the log of the accuracy on the y-axis, you almost get a line. And this is comparing, the decrease in the objective when you're performing exact line search. So you're picking the optimal step size, the one that you can figure out analytically, and the backtracking line search. So they're very similar. So this is actually confirming in a way the fact that we shouldn't probably bother most of the time in trying to figure out exactly the optimal step size. Backtracking is doing a fine job. The only caveat here is that the convergence rate depends on this constant c, and this constant c depends adversely on what's called the condition number of the function, so the ratio between the Lipschitz constant and the constant associated to the strong convexity. So the higher this ratio is, the closer c is going to be equal to, the closer c will be to 1, and so the lower the rate. Yeah?
How do these curves compare? The function is not strongly convex.
Oh, it's actually, so this, you remember if you don't have strong convexity, the rate is of the type big O of 1 over epsilon.
My question is, in that case, does the exact line search perform faster? If the function is not strongly convex, does the exact line search perform faster?
I think I wouldn't expect to be like dramatic differences, because again, it's a matter of how well you're approximating with backtracking the the location of the right step size, the optimal step size. This is just here to remind ourselves that if you perform backtracking, you're usually doing not much worse than performing optimal line search. So it's usually not worth it. Okay, any questions about this?
So in order to make use of these results, we need to find the Lipschitz constant.
That you'll never know it,
Right.
usually.
So it's just a statement that we need to.
So this is, in a way, is a theoretical guarantee for the algorithm. This is saying if you have convex function that is differentiable and it has Lipschitz gradient, you get a certain rate. If on top of that you also have strong convexity, you get a much faster rate. But of course, in practice, usually it's difficult to check whether your objective is or satisfies that properties. This is just meant to say, it's a theoretical guarantee on the algorithm in a way. Usually, you want to have a procedure that, under certain conditions, satisfies nice properties. This is what these theorems are about. Let me just go back a second to strong convexity, just to review it together. Again, strong convexity of f means that you can subtract a quadratic function to f and still get a convex function. And in the homework, you're going to show that this is equivalent to saying that if the function is twice differentiable, the Hessian minus m times the identity is still a positive semi-definite matrix for any x. And otherwise, you can also state it in the following form. You basically have a sharper lower bound than the one that you get from usual convexity. Usually from convexity, you only get this part. So the function is lower bounded by all of its tangent lines. Now, if you have strong convexity, you can also add a quadratic piece and get a sharper lower bound. Another way of that's it. So let's have a look at the conditions for an interesting simple problem, one which we encounter often enough. So the least square problem. So your function f of beta is just 1/2 times the square norm of y times some matrix x times beta squared. So Lipschitz continuity of the gradient means that if the function is twice differentiable and this is twice differentiable, that means that the Hessian of the matrix F at any point x minus L times the identity is negative semi-definite. And this constant L, since the Hessian is equal to x transpose x in this case, the constant L will be equal to, you can think about it as the largest singular value of x, or the square of the largest singular value of x, or the largest eigenvalue of x transpose x. Okay? So it's just saying, this is just saying how the constant L relates to this function, which is twice differentiable. It's basically, L is basically the largest eigenvalue of your covariance matrix, if you want. Whereas strong convexity of F, this is actually a little bit more of a strict requirement. This means that the Hessian of F, so x transpose x, has to be still positive semi-definite when you subtract m times the identity, or equivalently, the Hessian of F, which is x transpose x, has to have a minimum, so the smallest singular value, the smallest singular value for that matrix x has to be equal to m, and has to be larger than 0. And again, you can think of m as the square of the smallest singular value of x, or the smallest eigenvalue of x transpose x. And now here's the caveat. If x is a wide matrix, so you have x is n times p with p larger than n, so you have more columns than rows, like you observed more features than individuals in a way, then there's no way that the matrix x transpose x can have full rank. So it's going to be rank deficient, and your smallest singular value is going to be equal to 0. And if this is equal to 0, there's no way that m can be larger than 0. So for sure, if x is wide, f cannot be strongly convex. Is this clear? So usually this function is convex, in fact. But if x is wide, so if x is rank deficient, then there's no way that it can be strongly convex. Questions? Okay. So, and even if your matrix x is such that the smallest singular value is larger than 0, still you can have a very large condition number, meaning that the constant L divided by m, so the ratio of the largest eigenvalue to the smallest eigenvalue of x transpose x can be still very large. Okay? And that's impacting negatively the rate of convergence when you have strong convexity. Okay? And as a further reminder, now that we saw all these connections between strong convexity, Lipschitz gradient, and the Hessian, you can think about a function f having Lipschitz gradient and being strongly convex if you can sandwich the function between two quadratics in a way. So basically, this is saying that your Hessian, well, if you take L times the identity minus the Hessian, you still get a positive semi-definite matrix. And if you take the Hessian times minus m the identity, you still get a positive semi-definite matrix. So it means that the curvature of your function is basically sandwiched by two quadratics. It's about a quadratic function, basically. You can upper bound it by a quadratic, and you can lower bound it by a quadratic function. And as a side note, like this, requiring the function to have a Lipschitz gradient and being strongly convex is kind of a strong assumption. But we assumed when we were actually performing the proof, we just said, let's assume that this property is holding everywhere. But actually, it's enough to assume that you have this condition to hold on the sub-level set x, so the set of x such that your function is less than the objective value at the initial starting point. So you don't need the function to satisfy these requirements everywhere. You just need it on the lower, on the sub-level sets, on the sub-level set induced by your initial starting point, which is weaker, okay? So like, for instance, if you have a quadratic function, for instance, like x squared, no, that's a better example. But I mean, the point here is that you only need those properties to hold on a much smaller set and not everywhere. So any questions about that? Okay. Some practicalities. When do we stop? So the idea is to stop when the norm of the gradient is small, because if you have a convex function, at the optimum your gradient is going to be 0. Remember that we are performing unconstrained optimization, so this is a first order condition that has to hold. And it's necessary, but it's also sufficient if the function is convex. So this suggests that we want to stop when the size, when the norm of the gradient is small. And as a matter of fact, if you, for instance, if you knew that your function is strongly convex with parameter m, with that parameter m, if you stop when the size of the gradient, the norm of the gradient is less than the square root of 2m times epsilon, then you are guaranteed to have reached accuracy at least epsilon. Okay? So usually, of course, you don't know. It's hard to figure out that constant m, but this is just as a matter of fact, if you happen to know m, you have this implication. So what are the pros and cons of gradient descent? So definitely on the pro side, you have that gradient descent is a simple idea. We're just decreasing the function, like iteratively moving towards the direction of steepest descent. And each iteration is cheap because you only need to recompute the gradient at each iteration. So that's not very burdensome. Another good thing is that the algorithm tends to be very fast for well-conditioned problems. So if you have a strongly convex function and the ratio of the Lipschitz with the Lipschitz gradient and the ratio of the Lipschitz constant to the constant of strong convexity is small, then you actually have exponentially fast, a rate that is exponential. So that's good. On the downsides are that most of the interesting problems that we face are not well conditioned, so the algorithm can in practice be slow. And the thing is, the other downside is that you cannot handle non-differentiable functions. So far, the minimum requirement is that we have differentiability. So now there are a bunch of slides on forward stage-wise regression, which we encourage you to look at, because there are some interesting connection with gradient descent. So it's an application of gradient descent and a related procedure called steepest descent. That's basically gradient descent under a different choice of the norm, okay? And that's introducing also the concept of dual norm. We will discuss all these things again, but you are sort of encouraged to have a look at them by yourself and come to office hours if you have questions. The example that we're actually going to look at is gradient boosting. Let me check the time. If we may have a. No, we don't have time for that. So gradient boosting. The goal here is that you have. So this is an application of it's a tweaked application of gradient descent, which is actually interesting. So you're given a set of observational y's, y1 to yn. These are n-dimensional vectors. You can think of those as being, for simplicity, just scalars, just numbers. And you have a set of predictor measurements xi, which are p-dimensional vectors. So I is indexing the individuals. If you want, p is the number of features that you are recording. And for each of these individuals, you have a response y. And our goal is to construct a nonlinear model, nonlinear predictive model. It's a function of these predictors xi, and it uses trees. So we want our model to be a weighted sum of trees. So our predictor theta I for the response on the ith individual has to be a convex combination of trees with weights beta j. And we want to figure out the optimal trees and the optimal coefficient beta j's. So I don't know how familiar you guys are with trees, but they're relatively interesting objects. So the basic idea of a tree is that you need to figure out, how many variables you want to take into account in the tree, so how many branches. And the idea is that, for instance, if you take this tree, this first line might be the first variable, say x1. I need to figure out an optimal split, and then move forward, figure out a second variable, for instance, say x2, figure out an optimal split, and so on and so forth, until I reach a leaf. When I reach a leaf, the predicted value for y according to that tree is going to be the average of the values of y belonging to that leaf. Okay, you have questions about that, guys? Okay, so that's for one tree. Now, if I have more than one tree, I can get for the same predictor, for the same vector x, I can get more than one predicted value of y. And what I want to do here is to take an average of those, where the average is determined by this coefficient beta j's. So is the problem clear? Okay. So what we're going to do is we'll pick a loss function L that reflects our setting. So for instance, for a continuous variable response y, you can take the loss function to be a quadratic loss. And here I'm assuming that for simplicity that y is a scalar and not a vector, but you can extend it easily to the vector case. And you want to solve this minimization problem. You want to minimize over this coefficient beta the sum of the loss of predicting yi by means of this weighted tree, weighted combination of tree. And you're going to fix the depth of the tree, so the number of branches, in a way, the number of splits a priori. And if you were, for instance, to set it, say, to 5, even with a moderate number of features, you really, you have to search through a huge set of trees. So this problem is usually not computationally feasible or affordable, even for small depths and for relatively small number of predictors, because for each tree you need to you may just have a huge number. You can try and enumerate them, but it's a huge number of trees that you can search among. And so since we can just optimize over this huge space of trees, we're going to do something different. We're going to apply gradient boosting, which is a version of gradient descents that we will force to work with trees. Okay? And so I'll try and be clear about what we're doing now. So think about optimizing over the predicted values theta. So these are the predicted values for our responses y's. And we want to optimize over those by enforcing the predictors to come from trees. The prediction to comes from trees. So here it is. The algorithm works as follows. You start with an initial model. So you fit an initial tree T0 to your data, and that gives you a first prediction theta for your y's, for your responses. Then you will evaluate the gradient, let's call it G, at the latest prediction, theta k minus 1. So you're differentiating your loss of predicting y with the theta I coming from weighted sum of trees. And you evaluate that gradient in your latest prediction, and then you will find the tree, and the next tree that you will add is the tree tk that is closest to the negative gradient. So you want to solve this accessory minimization problem, so you're minimizing over all the possible trees, and you're picking the one that is more aligned to the negative gradient. Okay? So this is sort of it's sort of a gradient descent procedure. We are sort of trying to figure out what the gradient is, and we're trying to move in that direction. But we have an additional optimization problem that is forcing my gradient to be, I'm basically picking the tree that is most aligned with the negative gradient. Okay? So I'm trying to enforce myself to have a predictor that is based on trees. That's what I want. And so this is a problem that it's not hard to approximately solve, at least for a single tree. And then you will update your prediction in the gradient descent fashion. So your new prediction will be your previous prediction plus a step size alpha k times the latest tree that you found by solving this optimization problem. So this is actually very similar to gradient descent, but you're just trying to project in a way your gradient in the space of trees. This is different from projected gradient ascent, which we will see in the future, like in a couple of lectures, but it's sort of a similar idea. You're trying to, in the space where you're trying to minimize your function, you're trying to look for the element that is most aligned with the negative gradient. And then from this update equation of your predictions, it's easy to see that you end up with a prediction theta k that is a weighted average of trees. If you just repeat this update rule, you'll find out that theta k is going to be t naught, the first tree, plus alpha 1 t1 plus alpha 2 t2 plus alpha 3 tt plus alpha k tk. So we ended up with the type of predictor that we wanted, a weighted average of trees. Okay, so any questions about gradient boosting? Like it's a, yeah.
Just double checking, this is not a convex optimization problem.
Say it again.
Just double checking that this is not a convex optimization problem, because this minimization over the trees is not convex. Or is it?
That's an interesting question. That's an interesting question. I'm not sure that I can answer it now. We can talk about it later, unless Nicole or you guys have any. I'm not sure whether that's, technically I'm not sure how to characterize that minimization problem, if it's possible to have it as a convex minimization problem, but yeah. So let me quickly wrap it up. So we proved today that the rate of convergence for gradient descent is of the order 1 over epsilon. So if you want to have accuracy epsilon, you need about 1 over epsilon iterations when you have differentiable objectives with Lipschitz continuous gradients. And gradient descent is the building block of a family of methods that are called first-order methods. So we say that iterative methods that are first-order methods are those that are for which your xk, your update xk, is in this linear space. So this linear space spanned by x naught and the evaluations of the gradient of the functions at the previous iterations. So first order method is really just saying we're basically only using the gradient. We're searching through a linear space induced by the gradient. And there's a theorem by Nesterov that tells you that for any iteration k that is less than the size of the domain minus 1 divided by 2 and any starting point x naught, there is a function in the problem class. So the problem class that we consider is, again, strongly convex functions with Lipschitz gradients and that are differentiable, for which the accuracy that you get at the kth iteration is at least some constant times 1 over k plus 1 squared. This means that there seems to be a lower bound on the rate that tells you, in a way, you cannot hope that you can do better than 1 over k squared. And the rate that we figured out for the, or if you want 1 over square root of epsilon, if you want to have accuracy epsilon. And the rate that we figured out for the gradient descent was 1 over epsilon instead. So can we actually tweak the gradient descent and match this lower bound? The answer is yes. As Nicole mentioned before, you can do that by, for instance, introducing this acceleration technique. So we can match the upper bound on the rate and the lower bound. And actually, there's even more. There are methods, there are first-order methods that we will study that don't even require the function to be, you can handle much more complex functions. So functions that are not necessarily differentiable, for instance. Okay? So I think that's all that we have for today. Any questions before we leave? Good. Thank you, guys.